In this video, we're going to be talking about inverse relations. And first off, what is the inverse of a relation? It's simply a function. Let's actually say a relation, since we're talking about relations here. An inverse of a relation is a relation that reverses another relation. And we know that a relation is a set of ordered pairs, like if a point on a relation was 3, 5. That means when you plug 3 in, you got 5. Well, what is an inverse? Well, that would mean it would be a different function to where you could take every one of these y values and plug them in, and it would give you the x value. So it flip-flops them around. The notation that we use for inverses, the inverse of a relation R is written as an R with a little -1. Now, not to be confused with R to the -1 power. Okay, two completely different things, but that's the inverse relation. Give the inverse of the relation below, and again, an inverse does is it flip-flops your inputs and outputs. So if in our original relation we plugged in 0 and got -7, then the inverse would be some relation to where we could plug in -7 and give us 0. Okay, now for the rest of the points, I'm just going to switch my inputs and outputs again. -1, 2 switches to 2, -1. -4, -2 is now -2, -4. And 6, 3 is now 3, 6. So again, an inverse relation simply switches the input and output. It switches the x and y. Now find next up a one-to-one function. Okay, a function has a one-to-one relationship if a relation and its inverse are both functions. So the original relation has to be a function. Its inverse also has to be a function. If you don't remember what a function is, by the way, is each x is paired with a single y. An x cannot be paired with two different y values, but again, each x, there's no repeat x's. Each x is paired with a single y. Remember the vertical line test? You can't have an x above an x, okay? But now it's inverse, which actually switches it back around, which would mean that each y would actually have only one x as well. So again, recall the vertical line test is used to determine whether a relation is a function. The horizontal line test is used to determine if the inverse of a relation is a function. So pretty much now you can't have a point because you can't have repeat y's. You can't have a point next to a point, or you can't have a point over a point. If there's a point over a point, then it fails the vertical line test and it's not a function. If there's a point next to a point, that means its inverse would not be a function. Both the relation and its inverse must be a function in order to be one-to-one. Okay, determine whether the relations are one-to-one. So let's test to see, is this a function? There's no points above points, so it is a function. Let's test to see if its inverse would be a function. Now, we don't actually have to find the inverse. We just have to use our horizontal line test to see if there's any points next to points. Since this is a function and its inverse would be a function, yes, this is a one-to-one function. Number 2, let's test to see if it's a function. Vertical line test, it passes everywhere. That means there's no points above points. However, if we draw a horizontal line, the inverse is definitely, it would not have an inverse. It would not be a function. So therefore, no, this would not be a one-to-one function. So the original relation was a function, but the inverse relation was not a function. Next up, is this a function? This would be a function. The only question would be right in here. It has an asymptote line, but still there are no points above points, so therefore that would be a function. And the only time it gets close to being the inverse relation not being a function would be right in here. And again, that's an asymptote line. So therefore, if you draw a horizontal line here, it's still only hitting 1 point. So yes, this would be a one-to-one function. Here, it is a function, and its inverse is also a function. So yes, this would be one-to-one. This is definitely a function. However, if I were to draw a horizontal line right here, it hits every point. So no, this is not going to be a one-to-one function. Again, it's the original relation is a function. However, its inverse relation would not be a function. Then finally, this original is not even a function. So no. However, the inverse relation, if you were to invert this, the inverse relation would be fine, but the original relation is not a function. Okay, notation. Inverse functions. We've already talked about the notation for inverse relations. However, an inverse function, the inverse of a function is written as f inverse of x. So if you have a function that is invertible, the inverse of that function would again be written as f inverse x. That does not mean f to the negative 1 power. Not all functions have inverses. Okay, not all functions are invertible. It says to find the inverse of a function, replace f of x with y. They mean the same thing. We're going to simply interchange x and y. And that's what we've been doing, switching x and y, because, again, an inverse changes your input and your output. We're going to solve for y, and then we're going to replace it with f inverse, and that's it. Determine, first off, if f of x has an inverse. If yes, find f inverse and state any restrictions in the domain. So let's zoom in. And again, step number 1, we're just going to simply write this as y equals 4x minus 8. And the only reason we do that is so that we can switch our x and y. The inverse of this would be x equals 4y minus 8. Again, we're switching up our inputs and our outputs, so 4y minus 8. We then simply solve it for y. So to solve this for y, we're going to move our 8 over, and that's going to be x plus 8 is equal to 4y. We then get rid of the y or the 4 by dividing by 4, and you get y is equal to x plus 8 divided by 4. And now we can, instead of writing it as y equals, that is the inverse. F inverse is equal to x plus 8 all divided by 4, and that's it. Now, is there any domain restrictions? No, because you don't have to worry about any kind of division by 0. You don't have to worry about squares or negatives. Okay, the next one, number 8. Again, I'm going to replace f of x with y, so you have y equals 1/2 x to the third minus 1. In order to find the inverse, we simply switch our x and y. So what used to be a y is now an x, and what used to be an x is now a y. We're going to solve this for y, so we're going to move our 1 over. So I now have x plus 1 equals 1/2 y to the third. To get rid of 1/2 times, we're going to divide by 1/2, which is the same thing as multiplying by 2. So the other side becomes 2x plus 2. I went ahead and distributed equals y to the third. To get rid of a third power, we're going to cube root. So you have the cube root of 2x plus 2 is equal to y. But instead of writing equals y, we can now change that y back to f inverse. So f inverse is equal to this. And again, there are no domain restrictions there. Here, y equals x minus 4 squared plus 6. Now, I should have been checking this too as we went, but if you actually look, this is a function. The reason we know it's a function is because it says f of x. We can't use function notation unless something is a function. However, this function is not going to be invertible. The reason I know right off the bat it's not invertible is if you were to look at the graph of this. This is going to be a parabola. It's been moved right 4 and up 6. It looks like this. And yes, it is a function, but if you look at the horizontal line test, the inverse of this is not going to be a function. And the reason for that is if you were to switch x and y together, plugging in single outputs would result in multiple, plugging in single inputs would result in multiple outputs, so the inverse would not be a function. So since this thing is going to fail the horizontal line test, it is not invertible. So there is no inverse. Even though we can switch x and y, we can go through the process, it's not going to be an inverse function. Okay, number 10. Again, the same thing. Replace your f of x with y. So you have y is equal to 5 over x minus 8. To find the inverse, switch your x and your y. So we now have x equals 5 over y minus 8. Okay, now we've got to somehow get y by itself. Well, first off, we need it off the bottom of a fraction. So I'm going to take it and I'm going to, since it's divided by, I'm going to move it up here with my x. So I have x times y minus 8 is equal to 5. And instead of actually distributing it, I'm going to go ahead and move my x over to the other side. Since these are being multiplied, you can now say y minus 8 is equal to 5 over x. And it's going to be very easy now to get the y by itself by simply saying y is equal to 5 over x plus 8. Now that I've got it solved for y, we can now replace y again with f inverse. We can actually go back to the original, and I failed to do this, but this is a 1 over x type function. It's invertible because it looks like this. If you were to graph it, it's that type function, and that's going to be an invertible function. Now let's look at something that I didn't mention to begin with, but let's look at some domain restrictions. In our original function, x could not be 8, which means look at your final function. Let's see if there's any domain restrictions there, and there are some. The x value here could never be 0 because you cannot divide by 0. Okay. Number 11. Okay, let's look at those domain restrictions to begin with. First off, you can take your x plus 2 and say that it has to be greater than or equal to 0. Solve that, and that means your domain is x is greater than or equal to negative 2. So that means all values from negative 2 to infinity. That's the domain of this function. Now let's go ahead while we're at it, and I want you to do something else. I want you to find the range of that as well. The way that you can find the range is once you have domain, you can actually plug those values in, and you can see what happens. So my domain, my x values are negative 2, negative 1, 0, 1, 2, so on and so forth. As you plug those in, negative 2 and 2 is 0, square root of 0 is 0, negative 0 minus 7 is a negative 7. When you plug in negative 1, you're going to get square root of 1, which is 1, negative 1 minus 7, which is negative 8. And then plugging in 0, you would get something even smaller, smaller, smaller. So you notice that your y values there increasingly get smaller and smaller, smaller. So my y values would range from negative infinity up to negative 7. So now let's keep that up there, and now let's work the problem. To find an inverse, again, I'm going to write this as y equals the negative square root of x plus 2 minus 7. And let's switch our x and y's. X equals the negative square root of y plus 2 minus 7. Move your 7 over, and it gives you x plus 7 equals the negative square root of y plus 2. You can get rid of this negative by multiplying or dividing by negative 1, and you'll get negative x minus 7 equals the square root of y plus 2. To get rid of a square root, we're squaring, so that'd be in parentheses negative x minus 7 squared equals y plus 2. Move the 2 over, and you get negative x minus 7 squared minus 2 is equal to y. And again, you can change that y now to f inverse. Now let me explain why in the first step did I tell you to list both the domain and range of the original. Think about what you do. Whenever you find the inverse, you switch your x and y's. So what you're actually doing is you're switching your inputs with your outputs. These are your x values, these are your y values in the original function. So therefore, when you found the inverse, the domain of your inverse will be the y values of the original function because they're now switched. So therefore, the domain of this inverse function would be all values from negative infinity up to negative 7. So that is my domain restrictions now. Even though it doesn't look like there should be any restrictions, there needs to be in order to make this an invertible function. You have to put this, or because this would be actually a parabola, which normally wouldn't be invertible. However, when we restrict it, what used to be a parabola, when you say, well, we only want from negative infinity to negative 7, it makes it then an invertible function. Next problem. I don't have to even do this because you have an absolute value function. Absolute value functions do not have inverses because they fail the horizontal line test, so no inverse because, again, it fails the horizontal line test. Number 13, cube root functions are this type functions, so they are invertible, so we know that we can do these. So we have y equals the cube root of x minus 9 over 4 leads us to the inverse, which would be x equals the cube root of y minus 9 over 4. Let's get rid of our 4 first by multiplying. 4x is equal to the cube root of y minus 9. To get rid of a cube root, we're going to cube the other side, so that'd be 4x to the third power equals y minus 9. And I'm going to go ahead and write that as 64, which is 4 to the third, and x to the third. Move your minus 9 over by doing plus 9, so you have y equals 64x to the third plus 9, which we can again now write as f inverse is equal to. The original function, if you remember what I told you it looked like, the domain and the range were both negative to positive infinity, so therefore we have no domain restrictions there. Here, y equals 3x squared minus 1 is a parabola. However, what they've done is they've restricted the domain. So instead of a full parabola, and you can graph this because 0 is actually where the vertex is located on this one, you're going to have a half parabola. And since it is a half parabola, it is a function and its inverse, all of a sudden now it's invertible. Had you left it a full parabola, parabolas are not invertible. So that's the reason they restricted the domain here. Now what I would like to do again is not only give the domain, but I want to give the range that goes along with that. What are my y values? So the way we're going to find that, you can do a table or you can look at a graph. If your x values are greater than or equal to 0, well, let's plug in some. Plug in 0 gives you -1. Plug in 1 and it gives you 2. Plug in 2 and it gives you 11. So notice my values are increasing all the way to infinity. So my range will be all values greater than. You can write it either way. You can either say all the values from -1 to infinity, or you can just say y is greater than or equal to -1. That's going to be my range of my original. And again, hopefully you understand why we're listing that range. So my original function was y equals 3x squared minus 1. My inverse of that would be x equals 3y squared minus 1. Move the 1 over. Move the 3 over by dividing. Move the square over by plus and minus square rooting. So x plus 1 over 3 is equal to y. So that'd be f inverse is equal to that. However, we need to restrict. We need to say, okay, what is the domain of this? And again, the domain of my inverse function will be the same thing as the range of my original function. So y in my original had to be greater than or equal to -1. So now x has to be greater than or equal to -1 in my inverse function. Now here's the thing. Will I have the two possible values here? That's something else we really need to be careful of, is do I need to put the plus and minus? Because that might mess up my range here. And here's how we can determine that. X is greater than or equal to -1 is our domain. Look at the range now. Again, the domain and range is switched in this original. Now in my new function, my y value, which is f of x here, my y value has to be greater than or equal to 0. So therefore, it cannot be a negative. So we don't need this plus and minus out front, because if you had put that plus and minus, all of a sudden you've got this sideways parabola, which is not a function. So therefore, since my range has to be positive, that means we're going to take that plus and minus off, and we're only going to leave the positive ones. So there is your inverse function along with its domain.